Okay, good afternoon, everybody, and I welcome you again to the second talk of today afternoon. And this is the second part of the talk by Kavitha, who is a professor at the School of Technology and Computer Science at TIFR. Uh, and yesterday she told us about popular matchings and witnesses in two-sided preferences, as well as the popular assignment problem in the one-sided model. We'll learn more about it from her today in her second talk. So welcome to you.
Thanks, Meghna. And as this is the last talk of this workshop, on behalf of all the participants, let me take this opportunity to thank the organizers. Thank you. So I think it was a really nice workshop, and thanks so much for the effort you put in.
Our pleasure. I don't know where is Vikram and Oritra. Can you please unmute yourself?
Thank you. Thank you.
Thank you.
So let me begin. So this is a continuation of what we saw in the second half of my talk yesterday. We are dealing with one-sided preferences. So we have a bipartite graph. One side is a set of agents. Only they have preferences, only they cast votes. The other side are inanimate objects, as in this example. And the problem we were looking at is, does G admit a popular assignment? That is, we're interested only in perfect matchings here. And among perfect matchings, is there one that is not defeated by another perfect matching? So that's the popular assignment problem. And we also showed a polynomial time algorithm to solve it. So for the first maybe 15 minutes today, I would like to go deeper into proving the correctness of this algorithm. So let's just recall. So we use this edge weight function. Given a perfect matching or assignment M, there is a corresponding edge weight function as shown here. Weight of an edge is just, does the agent endpoint of the edge, that is, does A prefer the other endpoint to her assignment in M? If so, it's +1. If she in fact prefers her own assignment, it's -1. If she's indifferent, it's 0. And an assignment is popular if and only if a max weight perfect matching under this edge weight function has weight exactly 0. So this is the LP for max weight assignment. So by now, I hope you're familiar with this LP. And M is popular if and only if the optimum value of this LP is 0. So let's take the dual LP. It's a really simple looking LP. The variables are the alpha values. And we had this claim that M is popular if and only if there exists a dual feasible solution alpha such that the sum of all the alpha values is 0 and the alpha values of agents are in this set 0, 1, 2 till n-1, and the alpha values of objects are minus values of this 0, -1, -2 till -n-1. And then we introduced this subgraph G sub L. We said G has a popular assignment if and only if there is a level function L from the set of objects to this set 0, 1 till n-1 such that this subgraph G sub L has a perfect matching. So if it has a perfect matching, we claimed that was a popular assignment. And the proof of that was, in fact, we can construct a witness as shown here. So the alpha value of any object is the negation of its level, and the alpha value of any agent is the level of its partner. And if it has a popular assignment, it has a dual feasible solution alpha, and that would in fact define the levels of objects. So it's both ways. So let's just recall what is this G sub L. So given any such function L, we can define the corresponding subgraph G sub L. For any agent, let's define L star A to be the highest level at which it has a neighbor. And the edge set of this subgraph is exactly those edges AB between an agent and her most preferred neighbor at the highest level. And she's also allowed to look one level down, one level below the highest level. She can also put edges to her most preferred objects in this highest level -1, provided these objects are strictly preferred to her favorite objects in the top level. So let me just pause for a minute so that you can read what I've written here. EL has exactly those edges AB where level of B is the highest level for A, L star A, and B is the most preferred object for A in this level, or LB is one level below, and B is the most preferred object for A in this level, and A prefers B to all her neighbors in the top level. So the pseudocode of the algorithm was quite simple. Let's start with all objects on level 0. And while there is no object at level n, so while all levels are less than or equal to n minus 1, let's do the following. Construct the subgraph G sub L and find a maximum matching. If it's perfect, great, return M. That's a popular assignment. Well, if it's not a perfect matching, then we go to the step below where we say, let's increase the levels of all unmatched objects. And in case the level of any object becomes equal to n, we say return, there's no popular assignment. So in case we return a matching, the fact that it's a popular assignment is the easy side actually. So we can prove it's a popular assignment by constructing a witness for it, and the levels basically give us this witness. Alpha of B will be equal to minus of its level, and alpha of any A will be equal to level of its partner. And it's easy to show that this is indeed a dual feasible solution, and by construction, the sum of all the alpha values is 0. So let me go to the more difficult side. When the algorithm says G has no popular assignment, that indeed G has no popular assignment. So when does the algorithm say G has no popular assignment? It means the level of some object has reached n. So let's say L was a level function when the algorithm terminates. So L of B equals n for some object B. Now suppose G indeed had a popular assignment M prime. Let alpha prime be a witness of M prime. So the claim is, so let's look at the corresponding level function L prime, which is just minus of alpha prime B. We claim that for any popular assignment M prime and any witness alpha prime of M prime, our L function, our L value, the level of object B as per the level function L constructed by the algorithm is a lower bound of that L prime B. So the claim is L prime B is at least L of B. And so if L of B equals n, it means L prime B is also at least n. But that's a contradiction because by definition, alpha prime B has to be in this set. That's a definition of a witness, has to be in the set 0, minus 1 till minus n minus 1. So L prime B by definition has to be at most n minus 1. So if L prime B is at least n, that's a contradiction. So this some of this sort of minimality that this claim is showing is a very powerful property. So we are claiming that for any popular assignment and any witness, our L value is a lower bound for the level of any object under any assignment. So assuming the claim, if it is indeed the case that L value of any object equals n, then G has no popular assignment. Is this okay? So this is taking the claim as a black box. We'll prove the claim in the next slide.
Yes, sounds okay. Yeah.
So let's say at the start of any while loop, it is indeed the case that our current L value at the start of the while loop iteration, let's call it L subscript old. If L old B is less than or equal to L prime B for all B, then we will prove that by the end of this while loop, this remains an invariant, that this inequality is still maintained. And this inequality is certainly true right at the beginning because all L values are initialized to 0. So the technical lemma is that if an object B is unmatched in a maximum matching in G sub L, then in fact, this inequality is strict. It is the case that L prime B is strictly larger than L old B. So if you recall, we increase the level of an object only if it's unmatched in a maximum matching in GL. So for any unmatched vertex, any unmatched object B, because of the strict inequality, it has to be the case that L prime B is at least L old B plus 1. And L new B is exactly L old B plus 1. So the L value of an object changes only if it's unmatched in the particular maximum matching that we computed. So you should not say in a maximum matching, we should say in our maximum matching. And for any matched vertex, we let the L value alone. So at the end of the while loop, our inequality will still be maintained. So the lemma basically is claiming that the inequality is strict if, sorry, I should have kept saying our maximum matching. So please replace a maximum matching with our maximum matching, with the maximum matching computed by our algorithm. Yeah, so let's prove the lemma.
Kavitha, can I ask one question in the previous slide?
Please.
Yeah. So this first I itemized thing. So for any unmatched vertex B, now it's true by the way the algorithm was defined, L new of B, the new label of B should be L old of B plus 1 because B is unmatched, right? In the
Exactly.
current matching. But why should that be at most L prime B? L prime B is that solution that exists and the labeling with respect to that witness, right?
Exactly. So this is what the lemma is saying. The lemma is giving us this guarantee that it is strictly larger and they're all integral values. So it has to be at least L old B plus 1.
Isn't this that implication sign in the statement of lemma? Doesn't it mean that implies B is unmatched in a maximum matching in GL?
No, it's in our maximum matching. So
okay, implies L prime B is strictly greater than L old B, right?
exactly. So
So
if B is unmatched in our maximum matching, then it has to be the case that L prime of B is strictly larger than L old B, which means it is at least L old B plus 1.
are we not proving this lemma? We are taking this as a black box?
For now, we're taking it as a black box. In the next slide, I'm going to prove it.
Okay, so I was thinking that is the, okay, all right, thank you.
No. So this is a technical lemma. So
yeah. Okay.
the proof will take 2-3 slides.
Okay, so using this lemma, that thing follows directly.
Absolutely. So using the lemma as a black box, we are done. So the whole task is to prove this lemma.
Sure.
Exactly, a proof of the lemma. So again, let M be our maximum matching in G sub L old, and let B0 be an unmatched vertex, unmatched object in this matching. We need to show that L prime of B0 is strictly larger than L old of B0. So our matching is a maximum matching in this graph G sub L old. So the symmetric difference between M and M prime, it has an augmenting path because M prime is an assignment. It's a perfect matching. And M was not a perfect matching because it left at least one object unmatched. So let's look at this M augmenting path P, which has B0 as an endpoint. So there has to be some edge in this augmenting path that's not a part of our matching M. So let's call that edge ATBT, and let's examine the prefix of this augmenting path B0, A0, A1, A1, B1, so on and so forth. And the last edge, let's terminate this augmenting path till this edge BT80. So as shown in the figure, so just start from the top, B0, A0, dot, and let's focus till the last edge BT80. That is not, this edge is not present in our subgraph G sub L old. So M prime is a perfect matching in the corresponding subgraph G sub L prime. So if you look at this figure, the dashed edges are in M prime, the solid edges are in our matching M. So let's first show that L prime of BT, which is in fact the bottommost object in this path, the L prime value of that object is strictly larger than L old of BT. So let's first show that. Our whole job is to show that L prime of B0 is strictly larger than L old of B0. But let's start at the bottom and then we'll move to the top. So since this edge ATBT is not in the edge set of the graph G sub L old, so one of these three cases has to hold. Either AT has a neighbor in level at least L old BT plus 2, or it has a neighbor one level higher, that is L old BT plus 1, that's at least as good as BT, or it has a neighbor in the same level that's better than BT. That's why this edge is not present in our graph G sub L old. So that's the definition of the graph G sub L old. So if an edge is not present, it's because there is a neighbor at least 2 levels or even higher, or there is a neighbor 1 level higher that's at least as good as this object, or there is a neighbor in the same level that is even better. So suppose L prime BT equals L old BT. Since at the start of the while loop iteration, we had L prime B is at least L old B for all B. For each of these three cases, the conclusion is that the edge AT-BT should not be in E sub L prime either. And that's a contradiction because M prime is a perfect matching in G sub L prime. And so this edge is very much present in G sub L prime. So if it's the case that L prime of BT equals L old BT, then in fact this edge ought not to be present in the other subgraph either. But M prime is present in the other subgraph. M prime contains this edge, so this edge better be present, and the only way it can be present is that L prime BT is strictly larger than L old BT. So for the bottommost object in this augmenting path, well, for the entire augmenting path, but we're just truncating it till this portion. For the bottommost object, as far as this picture is concerned, L prime BT, its level under the L prime function is higher than its level under the L old function. And we show it actually the same inequality has to hold at every level. So let's move higher. Suppose there is an index I such that L prime Bi plus 1 is strictly larger than L old Bi plus 1. However, L prime Bi equals L old Bi. Then in fact, we again have three possibilities. And in each of these three possibilities, we get the same conclusion that the edge, the dashed edge AI Bi ought not to be present in G L prime either. So let's go through these three cases. So the edge AI Bi plus 1 is a solid edge that's present in our matching M. So AI has two neighbors, Bi and Bi plus 1. And this solid edge for sure is present in our subgraph. So it has to be the case that either its level is at least one or more higher than L old Bi, in the level of Bi, or it's in the same level as Bi, and AI does not prefer Bi to Bi plus 1, or it's one level lower, and in fact AI prefers Bi plus 1 to Bi. So if we assume that the level of Bi under that L prime function and under our function is equal, but Bi plus 1 had a higher level under the L prime function than our function, then in fact we get a contradiction. Because in the first case, the level of Bi plus 1 under the other function is at least 2 more than the level of Bi, both under that function. In the second case, Bi plus 1 is one level higher or more, and AI does not prefer Bi to Bi plus 1. And in the last case, it's in the same level, and in fact, AI prefers Bi plus 1 to Pi. So in all the cases, the conclusion is that AI Bi ought not to be present in that subgraph, G sub L prime. However, we know that the dashed edge is present in the other subgraph. So it has to be the case that if Bi plus 1 has a higher level under the other level function, then even Bi should have a higher level. So this moves upwards. All the objects on this truncated augmenting path that we saw have higher levels under the other level function compared to our level function. So finally, the topmost object B0 also has a higher value under L prime than our level function. So all this follows from the construction of our subgraph, really. So the construction of our subgraph gives us this proof. So going back to our algorithm, when we return G has no popular assignment, yeah, we're not making any mistake. G indeed has no popular assignment. And the running time of the algorithm, that's easy to see. So in every iteration, the level of some object is increasing, and we know no level can even become equal to n. So sum of all the levels is strictly smaller than n square. And so the running time of our algorithm, we keep computing maximum matching in every iteration. There are at most n square many iterations. So the running time is m into n to the 5/2. And as I said yesterday, this is perhaps a nice open question. Can we design a faster algorithm for the popular assignment problem? So now let's look at a slightly tougher problem. Suppose there is a cost function. So the graph has a popular assignment. Our algorithm is able to compute one, but there's also a cost function and there's a budget. And we would like to compute a popular assignment whose cost is at most the budget. So this is basically the min cost popular assignment problem. Can we do this in polynomial time? Unfortunately not. So this is an NP-hard problem, even when edge costs are in the set 0, 1, and agents have strict rankings. So while the popular assignment problem has a polynomial time algorithm, the min cost popular assignment problem is NP-hard. But let's look at a simpler variant of this problem. So this is a popular assignment problem with forced or forbidden edges. So we are given a subset of forced edges and a subset of forbidden edges. And we want to know if there's a popular assignment that contains all the forced edges and completely stays away from the forbidden edges. So a simple variant of our algorithm can solve this problem. So though the min cost popular assignment problem is hard, this particular variant, which is in fact a very well-studied variant in the stable matching literature, this is easy to solve. Easy in the sense there is a polynomial time algorithm. So let's look at this table. In fact, my theme in today's talk is basically filling the entries in this table. The complexity of finding a min cost popular solution. So let's focus on one-sided preferences. So the top right cell is basically saying what I said in the previous slide, the complexity of finding a min cost popular max matching. That's a min cost popular assignment. That's an NP-hard problem. However, the complexity of finding a popular assignment with forced forbidden edges, everything with one-sided preferences, we know the complexity. And the clean combinatorial characterization of popular matchings in one-sided preferences tells us that in fact, the top left entries, both the cells are polynomial time. So P is polynomial time. So let's focus on let's go back to two-sided preferences and ask the question, what is the cost of finding a min cost popular max matching with two-sided preferences? So we've not even defined this problem. So here we're given a bipartite graph and back to the starting model. Every vertex has a strict ranking of its neighbors. So this is the stable matching model. However, we're interested only in maximum matchings. So in fact, there are many applications for this problem, allocation problems in humanitarian organizations. So the cardinality is the most important attribute, more than stability, popularity, anything. Matching medical students to residencies, you can't just tell someone, I won't give you a residency because my stable matching left you unmatched, right? Everyone has to get matched. So in our example, in fact, the red matching, that's the only maximum matching here. That's the only feasible solution. So in fact, this problem was considered a few years ago by Biro et al. And they asked, what is the complexity of finding a maximum matching with the minimum number of blocking edges? So in fact, this problem arose in Scotland when they had to match medical students to residencies, and a stable matching was leaving some of them unmatched. And so they were asked to find a maximum matching with the minimum number of blocking edges. So they could do it for that particular instance, but they wanted to find the complexity of this, and they showed its NP hat. So this is a very natural relaxation of stability, and unfortunately, it's hard. So how about a popular maximum matching? So this is a matching that's popular, restricted to the set of maximum matchings. So if you look at the red matching, it loses to the blue matching. So it's not popular absolutely. So smaller matchings may defeat it, but it is undefeated by maximum matchings. So does such a matching always exist? So in one-sided preferences, for sure it doesn't exist. And the whole algorithm was to decide if one exists or not. But in two-sided, and we are in two-sided strict preferences. So in two-sided strict preferences, does such a maximum matching always exist? Can we find one easily? So actually, I looked at these questions about 10 years ago in the same paper as the max size popular matching algorithm. So the same paper has both that algorithm and this algorithm where, in fact, I showed that such a popular maximum matching can be computed in order mn time. So such a matching is always there because the algorithm finds it. So let's just go through this algorithm. It's just a simple algorithm. Every vertex has a level associated with it. Every agent, so let me stick to the same notation. Let's call maybe agents and objects is not fair here. It's not fair here because vertices in B also have preferences and votes. Okay, so let's just go around calling them vertices in A and vertices in B. So every vertex in A has a level L of A associated with it, and every vertex in B prefers higher level neighbors to lower level neighbors. So in fact, that algorithm that we saw for popular assignments, we can say is a kind of borrow some ideas from this one. So we initialize the level of all objects to 0. And at the end, the level of not all objects, sorry, all vertices in A, they're initialized to 0. And at the end, L of A is in this set 0, 1, 2 till n minus 1. Sorry, I'm saying objects somehow by just some habit from the previous algorithm. There are no objects here. Both sides have preferences. So the popular maximum matching algorithm is as follows. Let's run the Gale-Shapley algorithm in the given instance. If this is perfect, wonderful. So while there is an unmatched vertex in A, whose level is strictly smaller than n minus 1, increase its level and it starts proposing to its neighbors all over again. And the Gale-Shapley algorithm continues. So an agent who has been rejected by all its neighbors in level 0 gets promoted to level 1 and starts proposing again. And because vertices in B prefer higher level neighbors to lower level neighbors, a neighbor who rejected this agent in the first round may now find it more interesting and accept it. And the algorithm continues. So return the final matching. So it's not clear that the final matching is a maximum matching, let alone a popular maximum matching. But yeah, so you could look up this paper. It's not a hard proof of correctness, but I won't be doing it here. My focus now is on this question, is on the min cost variant of this. Suppose it is a cost function and a budget. I know how to find some popular maximum matching, but I want to find a min cost one, something that's within my budget. Can we do this efficiently? For popular assignments, the answer was it's NP hard. However, here, the problem can be solved in polynomial time. So the popular maximum matching algorithm, though we wrote it as it's just running Gale-Shapley algorithm across n levels, we could imagine it as running one invocation of Gale-Shapley algorithm on a graph which can be considered as n copies of G taken together. What do I mean by this? So let G star be the graph where every edge is replicated n times. So if you recall the bidirected graph that we saw last time, where every edge was replaced by 2 edges. Now let's replace every edge with n copies. So rather than 2 copies gave us the max size popular matching algorithm. And if we replace every edge with n copies of itself between the same 2 endpoints, so in fact, Gale-Shapley algorithm on this graph gives us a popular maximum matching. So is this G star graph sort of clear? So So there are n copies. There we put directions on edges. So here let's attach a level to each version of the edge. So there are n copies of this edge. One copy I'm calling level 0 copy, another copy I'm calling level 1 copy, and so on and so forth, level n minus 1 copies. So each of these copies of the same edge E has a different level associated with it. And vertices in A prefer lower level edges and vertices in B prefer higher level edges. So between the same two endpoints A and B, there are n copies of the same edge. A says, I like the level 0 edge better, and B says, I like the level n minus 1 edge best. So any vertex in A likes all level 0 edges better than all level 1 edges, and within level 0 edges, it's her original preference order. Within level 1 edges, it's her original preference order, so on and so forth. And vertices on B, on the other hand, say any level n minus 1 edge is preferred to any level n minus 2 edge, which is better than any n minus 3 level edge, and so on and so forth. And finally come level 0 edges. So the proof of correctness of the previous algorithm shows that any stable matching in this graph G star maps to a popular maximum matching in G. So what we showed in this paper last year was this mapping is surjective. That is, every popular maximum matching has to arise in this manner. So yesterday someone asked me this question: if every max size popular matching arises as a stable matching in that bipartite graph, and the answer was no. However, for popular maximum matchings, interestingly, every popular maximum matching arises exactly as a stable matching in this graph, where every edge is replicated n times. So that's what the surjectivity means, that every popular maximum matching, in fact, can be viewed as a stable matching in this graph G star. Which means to find a min cost popular maximum matching, all I have to do is find a min cost stable matching in G star. And there are many algorithms for this problem. Efficient combinatorial algorithms, linear programming based algorithms. This is a very well studied problem. So by using this algorithm, I can solve the min cost popular maximum matching problem. Is it okay so far? Yeah, so we're given a popular maximum matching M. Our goal now is to come up with a level function. So I said the level function is on the edges, but it would be simpler to think of it as on the vertices. So we want to come up with a level function on the vertices so that I'm just saying something here, M and L satisfy stability in G star. What exactly this line means, I'll explain in the next slide. But for now, let's just recall this edge weight function. We are in the world of two-sided preferences. So given a matching M, there is a corresponding edge weight function, which gives every edge a weight of either +2, -2, or 0. Blocking edges get a weight of +2. And if both the endpoints hate each other compared to their respective partners in M, it gets a weight of -2, otherwise 0. So what does it mean to satisfy stability in G star? So I've just drawn the matching as, so AI and BI in the figure just represent vertices whose level is I. So what does it mean for M and L to satisfy stability in this graph G star? So for any matching edge AB, the levels assigned to the endpoints of any matching edge have to be the same. So that would be in a way the level of the edge I was referring to earlier. So if AB is in the matching M, then L of A has to be equal to L of B. And unmatched vertices in A have to be in the topmost level, and unmatched vertices of B have to be in the bottommost level. And for any edge AB, it should be the case that level of B is at least level of A minus 1. So for an edge to move to a higher level, she tried with all her neighbors and they didn't find her current level interesting. That's why she had to get promoted to the highest level, to the next higher level. That's what this constraint is capturing. L of B should be at least L of A minus 1. And for two vertices in the same level, in fact, the edge between them cannot be a blocking edge. The edge weight has to be either 0 or -2. And for an edge AB, where B is one level below A, their edge has to be a kind of hating edge. Both of them should hate each other. So their weight is -2. So this is what it means for a matching M and a level function L to satisfy stability in G star. So we want to claim that given any popular maximum matching, so we're given a matching M, and we're also told it's a popular maximum matching, I can actually construct such a level function so that all these properties are satisfied by that function L. That's our claim. So let's go back to the LP method. And for simplicity to begin with, let's assume that G has a perfect matching. And let's write the LP for max weight perfect matching. It's a very simple LP. So every vertex has to be matched. So summation xc E belongs to delta U is equal to 1. And if M is a popular perfect matching, then the optimum value is 0. The dual is quite simple. We are not familiar with this. So if M is a popular perfect matching, then there is a dual feasible solution alpha such that sum of all the alpha values is 0. We show, in fact, there's an optimal solution with more structure. So alpha of A is in the set 0, -2, -4 till -2 times n minus 1. And alpha of B is in the set 0, 2, 4 till twice n minus 1. So let's set the level of a vertex in A to be I if its alpha value is -2i. So just drop the -2 and take the I. And for a vertex in the set B, set its level to be j if its alpha value is 2j. And actually this works. So the levels that you were looking to construct are actually just being produced by the dual LP. So we wrote the dual LP totally in a mechanical manner virtually, but there is so much meaning in these values. So there is a very nice structured dual optimal solution, and we can actually read out the levels from that by just halving these values. And the tougher case is when G has no perfect matching, in which case we need to set L values so that all unmatched vertices in A are in the topmost level and unmatched vertices in B are in the bottommost level. So we again play with the dual LP. So we just drop all the unmatched vertices for now. Then it becomes a perfect matching in the resulting in the remaining graph. So we can just inherit the previous lemma. And now we also claim that for all neighbors of unmatched vertices, in fact, we can pin down the alpha values. Rather than say they just belong to this set, we can say that for all A that are neighbors of unmatched vertices in B, alpha value has to be 0. And for all B that are neighbors of unmatched vertices in A, alpha value has to be twice n minus 1. So the alpha values of neighbors of unmatched vertices have to be the highest possible alpha values in both these sets. The highest possible alpha values for vertices in A is actually 0, and the highest possible alpha values for vertices in B is twice n minus 1. And these vertices that are neighbors of unmatched vertices claim the highest possible alpha values. So this is in fact a technical lemma. And now we set alpha, the L values exactly as before. Just take half the alpha value, take absolute value, and yeah, this works. So the toughness here was to prove the lemma, the existence of such a dual certificate.
May I ask a question? Okay, just looking at this pink magenta text. So it's fair to say that, is it fair to say that vertex has high alpha values, that level information, because it couldn't find a partner in the lower levels?
So vertices in A always want to be in lower level, exactly. So for them, there is no need to go upwards at all because they in fact even have unmatched neighbors. So a vertex has to actually move, a vertex in A will move upwards only if she can't find a neighbor, only if she can't find a partner.
What about the B vertices?
So B vertices like to be in as high a level as possible. So they would ideally like to, in fact, propel themselves to the highest possible level. And in fact, they have unmatched vertices who have to keep going higher and higher and higher to find partners. So thanks to such neighbors, they get to move upwards. So there's those neighbors who are desperate and have to move to the highest level, and even there they have not been able to find partners, will naturally keep asking these people again and again and again, will you be my
Yes.
partner? Will you be my partner? And so these people have a lot of, let's say, value in the market because they have neighbors who are ready to do everything to please them. And these people say, well, I want to be in the highest level. These people say, yes, I'm ready to go to the highest level. But even then, they couldn't find partners, these unmatched vertices. Nonetheless, the neighbors have partners at least as good as them, in fact, better than them, because we're in the strict preferences. So it's very intuitive, right? Yeah, but
Right.
to prove it is
Like this, they have to climb up if they couldn't find lower neighbors, and they have to come down if they can't find neighbors, right? And at some point, if they meet each other, that's when the matching happens.
exactly. But here there are unmatched vertices, so these poor people could not find partners. So.
Right. So this B being a neighbor of an unmatched vertex in A, so all these unmatched neighbors are at the highest level, and this B alpha B who's realizing this 2 into n minus 1 thing, it has already found a partner, right? Otherwise, why should this person be unmatched? Why it should
Exactly.
have it, right, unmatched neighbor? So it must have found a neighbor at one of the higher levels so that it be
At the highest level.
at
So
the
higher
highest
the
level,
better.
right?
Exactly.
That's why they have a unmatched neighbor at the highest level. Otherwise, yeah, okay, yeah,
Exactly.
all right, okay,
Exactly.
thank you.
Yeah, all this is very intuitive indeed. I'm glad you're able to visualize it indeed. Because when you look at the algebra, it just looks like some symbols, some values, but there is a story also.
Yes, that's yeah, but I think you explained it nicely to sort of understand
Thanks.
what's happening.
So Meghna, how much time do I have left?
Yeah, so we have 20 minutes.
Okay, thank you.
Yeah.
Yeah, so I wanted to fill up more entries in this table. So in the bottom right cell, I wrote 2P's because we proved that the min cost popular maximum matching problem can be solved in polynomial time, and forced forbidden edges is a special case of it. So that's also in polynomial time. So we still have to fill out these cells. So let's look at two-sided popular matchings. So there is no condition on cardinality. It's not that cardinality is better, is more important than popularity. We are in the starting model. It's only popular matchings we are interested in. Let's try to see the complexity of finding a popular matching with forced or forbidden edges. So in fact, this was our working example there. And we constructed this bidirected graph yesterday, if you recall. And in fact, we ran the Gale-Shapley algorithm here, and we said any stable matching in this bidirected graph is a max size popular matching in the starting graph. So let's call such a popular matching dominant. What is the characterization of dominant matchings? These are popular matchings that defeat all larger matchings. So not only is the matching popular, popular just means you're not defeated, but these matchings actually defeat all larger matchings. So that's the class of dominant matchings. So in fact, this is a dominant matching, the green one in the top figure. Suppose we are given a single edge E and we want to know if there is a popular matching that contains this single edge E. So this is joint work with Agnes J. So basically, this is a very well-studied problem in stable matching literature. There are linear time algorithms, simple variant of the Gale-Shapley algorithm that checks if there is a stable matching with a given edge. If there is such a stable matching, great, return the stable matching because that's popular. Otherwise, let's try to find a dominant matching with a given edge. How do we solve this problem? Any dominant matching is a stable matching in G prime. So run the same stable matching with a particular edge algorithm in G prime. If we find such a stable matching, great. That's a dominant matching. It's a popular matching. So we've solved the problem. If we can find neither a stable matching with E nor a dominant matching with E, we claim there is no popular matching with E. And in fact, we show a decomposition theorem for popular matching, and that leads to the correctness of the algorithm. So I won't prove the correctness, but I think it's a nice algorithm. Just 3 steps. Check if there is a stable matching, check if there's a dominant matching. Otherwise, there's no popular matching. So this was a nice story as far as a single edge was concerned. But what about if you are given 2 edges? Is there a popular matching that contains both these edges? Note that there need not be a stable matching with both the edges or a dominant matching with both the edges. There could be a popular matching, but our decomposition theorem says it splits into a stable part and a dominant part. Maybe the stable part has E1 and the dominant part has E2. So it's not that the stable part has both E1 or E2, both E1 and E2, or the dominant part has both E1 and E2. In fact, this is an NP-hard problem. So the minute we go to two edges, is there a popular matching with both these edges? We don't know how to solve it in polynomial time. In fact, it's highly unlikely it can be solved in polynomial time. So in fact, the set of popular matchings, the complexity is sort of quite strange, I feel. So I just marked at the top, we have the set of max size popular matchings. At the bottom, we have the set of min size popular matchings. We know how to find a matching in these classes. The Gale-Shapley algorithm in G prime and in G finds these matchings. However, is there a popular matching that's neither max size nor min size? So in that entire part in the middle, is there even a single matching or is it empty? Just to answer this is an NP-hard problem. So the complexity is like this. Finding a max size popular matching is easy. Finding a min size popular matching is easy. But trying to find something that's neither max size nor min size is NP-hard. So now we can fill up the last entry also. So in fact, with even two forced edges, it's NP-hard. For sure, the min cost popular matching problem is even harder in the sense. If even the special case is NP-hard, the general version is of course NP-hard. So we have filled out all the entries, and strangely, the two-sided preferences popular matching problem has turned out to be the hardest of the lot. So both the cells for that are NP-hard. So this motivates, why not relax matchings to fractional matchings? Yesterday in Amit's talk, we saw he was doing fractional set cover. Today, Siddharth was doing again fractional allocations. So similarly, we'll do fractional matchings. So let's say we have students and advisors, and we want to match them optimally. Of course, we don't know how to find a, let's say, max utility or min cost popular matching. But maybe student can have two advisors. So his half advisor is A, half advisor is B. Maybe we can come up with a fractional allocation, fractional matching that somehow optimizes how well things can pair up with each other. So what is a fractional matching? So the convex hull of the edge incidence vectors of all matchings, that's a matching polytope, is described by these constraints. And any point in the matching polytope is a fractional matching. So it's a vector in Rm that satisfies all these constraints. And it can be expressed as a convex combination of, so I subscript mi is just the edge incidence vector, the 0, 1 vector corresponding to a matching mi. So X can be expressed as a convex combination of some matchings. And the notion of popularity extends to fractional matchings also. So to compare a fractional matching with an integral matching n, let's just write X as a convex combination of matchings and just take the corresponding, let's compare each of these mi's. Let's take delta. Delta was the difference between the number of votes that mi wins and n wins. Yeah, Sushmita?
So this representation, decomposition of a fractional matching into integral matchings, is there a basis set or is there any?
Oh, indeed. So I'm coming to that. Just you're slightly faster than me. Exactly. So let's define it like this. This was like a natural way of defining it. I wanted to say that delta x comma n is just the way, if I write x as summation pi mi, let's just write delta x comma n as summation pi delta mi comma n. And let's say fractional matching is popular if delta x comma n is non-negative for all matches n. However, as Sushmita pointed out, maybe X can be written as a convex combination of many matchings in many ways. It's not unique. So why is this well defined? Why is delta X comma n the way I wrote it? Maybe it can be written as a different convex combination of some other m prime i's, and then it doesn't seem to be a rigorous definition. So let's redefine delta X comma n In fact, in the way we define it for matchings, let's have an edge weight function, weight subscript x, where x is a fractional matching, where we say the weight of this edge AB under the fractional matching x is just the sum of votes of the endpoints of the edge for each other versus the respective assignments in x. So basically, it's just the sum of these votes, and I've tried to illustrate what A's vote for B versus its assignment in X is. Look at, let's put self loops also so that every vertex is perfectly matched. And so it is just sum of the values it has along edges or neighbors that are strictly worse than B minus the sum of X values it has along edges for neighbors strictly better than B. It is just by linearity. And in fact, what we defined in the previous page, which looked like a natural definition, and this definition, they coincide. So this is joint work with Julian Mestre and Meghna, who is the chair. So in fact, we extended the notion of popularity to fractional matchings in this paper. So both the definitions of delta x comma n are the same. So what looks like a natural definition but may not look rigorous is actually fine, because we could have redefined delta x comma n as, let's just take the sum of votes of all vertices in the manner given here along the edges given by n. So n tilde is just basically, let's just put self loops and so on. So let's just stick with the previous definition because that's more natural, we could say. Either way is fine. So we define what's a popular fractional matching. It's a fractional matching that never loses an election against any matching. So delta x comma n is non-negative. So let's look at this simple example where there's only one popular matching, that's the blue matching. However, the fractional matching given by half along the value of half along the two blue edges and a value of half along the two red edges, that's also popular. One can check that it does not lose any election. However, the red matching is unpopular. So you can have a convex combination where some unpopular matchings are participating in the convex combination, but the resulting convex combination is popular. So as far as integral matchings are concerned, there's only one popular matching, but fractional matchings we're able to find. So the red matching is able to combine with the blue matching, and somehow they're able to form a popular combination. So how do we describe the convex hull of all popular fractional matches? It's not integral because there are these fractional matchings that cannot be expressed as convex combination of popular matchings. So we can write it down in the following manner with exponentially many constraints. Delta x comma n is non-negative for all matchings in the given graph. So there are exponentially many constraints, and the remaining constraints are just the matching polytope constraints. So now let's go back to witnesses and show, in fact, there is a much nicer way to formulate this polytope. Rather than these exponentially many constraints, we can come up with, in fact, only linearly many constraints, a compact extended formulation. We'll introduce new variables now. And so let's take a fractional matching x. So if x is a popular fractional matching, it's an optimal solution to this LP. So here the variables are the y sub e's. So x is one particular fixed fractional matching. X is not a variable, y is the variable here. Let's take the dual LP. So even a popular fractional matching has a witness, that is a dual optimal solution. So, and now let's stick with this dual LP. And instead of fixing this fractional matching x, let's allow x to just move along the matching polytope. So let's make x also a variable here. And that gives us this polytope, which is in fact a compact extended formulation of the popular fractional matching polytope. So this is a much simpler, it has only linearly many constraints. So I just took the dual LP and I also forced that alpha has to be an optimal solution. So summation alpha u is 0. And x is not fixed. It's not a fixed fractional matching. I'm allowing it to be any fractional matching. So the variables here are both x and alpha. And this polytope actually looks quite similar, I would say, to the stable matching polytope, which is a classical object which was formulated many years ago, 30 years ago. So whose constraints are linear. I've just written it as weight subscript x AB is at most 0 for all edges AB, and that weight subscript x of AB is just what I've written below. It looks a little complicated, but just a linear. It's just the sum of votes of A and B for each other versus the respective assignments in X. That's all. And the compact extended formulation of Fg of the popular fractional matching polytope is a natural generalization of it, where instead of, if we hard code alphas to be 0, what we get is the stable matching polytope. Instead of saying the weight of every edge has to be at most 0, we're saying the weight of every edge has to be at most sum of alpha values of its endpoints, and sum of all the alpha values across all the vertices has to be 0. So the stable matching polytope is the case where all alpha values are 0. And when you allow this extra degree of freedom, what you get is a popular fractional matching polytope. So we didn't design this popular fractional matching polytope keeping the stable matching polytope in mind, but it has turned out to be a very natural generalization. I just wanted to show that. So by optimizing over the popular fractional matching polytope, we can find a min cost popular fractional matching in polynomial time. However, it has become maybe difficult to implement, right? We said a student can have 2 advisors, he can be 2 half advisors. But maybe the optimal solution is going to give us solutions like 2 over 17. What does it mean to have an advisor 2 over 17 times or something? So is there a better structure to an optimal popular fractional matching? So we show indeed there is, in fact, a lot of structure. The linear program that led to the compact extended formulation has a very nice property. It is self-dual. That means some nice complementary slackness conditions hold, and that allows us to show this polytope is half integral. So indeed, you will get an optimal solution where a student can have just 2 advisors and each of them is like half an advisor. So let's just quickly see the proof of half integrality. How much time do I have, Meghna?
Yeah, you have 5 minutes.
Okay, then let me finish in 5 minutes then. So let's look at a popular fractional matching X, and let's look at all the fractional values with which it gets assigned to various neighbors. So let's look at the special case when G has a perfect stable matching. In this special case, we'll show that the popular fractional matching polytope is integral. So for any vertex in A, let's arrange all the entries in this fractional allocation in increasing order of A's preference. So X has a witness alpha. I'm using that alpha to split this array into 2 parts. The first part I'm calling of length 1 plus alpha A by 2, I'm calling the blue subarray, and the remaining part I'm calling the red subarray. Now let's swap the blue and red subarrays to get a reordered array. Let's call it X prime. And the order within the blue and red subarrays is preserved. Let's do an analogous transformation for vertices in B as well. So here, the entries are arranged in decreasing order, and the initial 1 minus alpha B by 2 fraction will be called the red subarray. The rest of it is called the blue subarray. We swap the red and blue subarrays again. And let's form a table whose rows are these reordered arrays X prime. So X prime arrays for all the vertices are arranged one below another. And let's sweep a vertical line along the table and decompose it into columns as shown here. As soon as you hit a cell wall, freeze. That defines a matching. Again, start moving the line. You hit a cell wall, freeze. That's your second matching. Again, keep moving the line. You hit a cell wall, freeze. That's your third matching. So we get, in fact, it's not clear it's a matching. So we show that, in fact, each of these MIs is a popular matching. So this popular fractional matching can be written as a convex combination of popular matchings, which was not the case in that example we saw. That's because G has a perfect stable matching here. That example, there was no perfect stable matching. So in this special case, in fact, the popular fractional matching polytope is integral. when G has a perfect stable matching. And this will imply half integrality in the general case, which means there is always a min-cost popular fractional matching that's half integral. This is joint work with Chilchung Huang. And finally, I wanted to use this integrality in the special case to get a result on approximately popular matchings. I'll finish it in 2 minutes. So can we relax popular to approximately popular for the sake of tractability? Popular means no matching wins more votes than this matching. Let's call a matching quasi-popular if no matching wins more than twice as many votes as M. Can a min-cost quasi-popular matching be efficiently computed? Unfortunately, this is also hard. So in fact, both the min-cost popular and quasi-popular matchings are NP-hard to approximate a penny factor. So let's ask for a bicriteria approximation. Can we efficiently find a quasi-popular matching of cost at most that of a min-cost popular matching? And here we finally have a positive answer. So the popular matching polytope and the quasi-popular matching polytope both have near exponential extension complexity. To describe these polytopes, we need exponential size. We're able to show an integral polytope sandwiched between these two that is easy to describe. And optimizing over this leads to that efficient bicriteria algorithm. This is joint work with Yuri Feinzer. So we'll be using this result that if G has a perfect stable matching, then its popular fractional matching polytope is integral. So let's just, in fact, the given graph need not have a perfect stable matching. Let's just augment G with some new edges so that the resulting graph G star has a perfect stable matching. And in fact, the popular matching polytope of G star is easy to describe. That's what we saw in the previous case. Because in this special case, the popular fractional matching polytope is the same as popular matching polytope. So,
can I ask a quick question?
Sure.
So if graph G has a perfect stable matching, shouldn't all popular matchings be stable or at least perfect?
Yeah, they're perfect. That's true.
But they need not be stable. That's one.
They need not be stable, exactly.
Given that the stable matching polytope also has a self-duality property, right?
Exactly. So not as exactly as self-duality, but something very close to self-duality, exactly. But then we could have non-stable perfect matchings also turning out to be popular. So I cannot use that.
That's the case that you're able to capture using
exactly
the popular, those
absolutely
things.
So those alpha values are giving that extra freedom in a way. So indeed, yeah. So this is really the last slide. So we are showing that every popular matching can be extended to a perfect popular matching in this augmented graph. So we have the popular matching polytope, that's a red figure. We've in fact, this is a subset of the popular matching polytope in G star. And we show every popular matching in G star when restricted to edges of G is quasi-popular. So that's how we get this sandwich polytope. So that's all I wanted to say. And thank you. So I tried to cover a lot of work today. Sorry if it got a bit heavy. So these are all my collaborators in these papers. And thank you.
Thanks a lot, Kavitha. And yeah, your dot on time.
Oh, thank you.
So I have one follow-up question on what Sushmita asked. So when we are in this case where G has a perfect stable matching, we don't encounter the case that a fractional popular matching is made up of an unpopular matching.
Exactly. So all we are saying is, Meghna, all we are saying is maybe it can be written as a convex combination of unpopular matchings also, but there is also a convex combination using popular matchings. Exactly.
So we can say that Burger-Newman decomposition works for this class of popular.
Exactly. So the popular fractional matching polytope is integral in this case. So any popular fractional matching can be written as a convex combination of popular matchings. So when G has a perfect stable matching, things are very easy.
Not easy, relatively speaking. No, and I wanted to say that we have so many papers and on so many while doing so you did an amazing job of covering a huge sort of landscape. So thank you.
Thanks. I'm glad you liked it.
I'll ask if anybody in the audience has any question. Okay. So if not, we'll thank once again Kavitha for the wonderful sessions to talk.
Thank you.
And
Thank
thanks
you.
to the organizers for arranging this wonderful workshop.